Hello and welcome to Easy Projects. A lot of you seem to like the chip chat video, so here's another one for you, and it'll be number 4. Today we're going to talk about this chip. It's an analog multiplexer slash demultiplexer, also sometimes called an analog switch. And it is in many cases very similar to this, which is a standard rotary switch. And to those of you who might not know such a switch, it's basically you have one common pin in the middle that you can solder a wire to, and when you rotate this, you alternate between connecting this pin to, for example, this one, the next time this one, this one, this one, and so on. This particular one has 12 pins and one common pin, so it can make 11 clicks. You can also get them with 2 common pins, and then it will have 6 pins that will connect to this and 6 pins that will connect to the other. And it will switch both pins when you turn this, and then you only get 5 clicks. If we look at the Texas Instrument datasheet for this chip, which is the CD4051, and you can also get the 52 and the 53. The 51 is the one in the top here, and you can see it works just like our rotary switch. You have one common pin that can connect to these other pins. In this chip there's 8 pins. But instead of rotating a knob like you do in this one, it's digitally controlled, of course. And you can see this number here that goes from 000 to 111. Select which channel is connected to the common pin. We also have a master disconnect over here, so you can just disconnect the common pin from anything. The 52, you just have 2 common pins, and it switches the pair between this one, this one, this one, or this one. And the 53 has 3 common pins, but it can only alternate between 2 sets of inputs. The chip we will be looking at is the 51, and that's the one I have right here. I'll also quickly mention that these chips can be used both ways, so you can send the signal either from the common to the selected pin or from the selected pin to the common pin, hence the name multiplexer slash demultiplexer. Some chips called multiplexers can only do it from the common pin and out to the switched one, and demultiplexers only the other way, or at least some of them, but this can do both ways, just like the mechanical one here. So what I'm going to use this chip for, and I'll show that in another project, is to read the voltages of a whole lot of lithium-ion cells with a Arduino Nano microcontroller. The microcontroller only has 8 analog channels, but I need to read 12 cells. So I'll have to switch them in somehow, and this chip was the first that came to my mind. And I thought it would make a good video explaining how it works. So the reason I want to build that voltage reader is because I had 2 of these lithium-ion batteries, but one of them failed on me. But I just measured the voltage across the entire battery, and it turned out one of the cells were bad in the other battery, and that ended up squealing because it probably over-discharged that cell. I mean, it shouldn't have done that if the battery was in good condition, because it should drain the cells evenly. But I just don't want to risk another battery squealing and potentially catching fire, so that's why I'm building this little unit that can continuously check all the voltages to make sure that everything is okay. I'll of course be uploading all these videos when they are finished, so you'll see this unit being made and you'll see the final project as well. And now that we're talking about microcontrollers, the way the ADC works in this is quite similar to this chip actually. You have 8 analog channels on this Arduino Nano, but in fact there's only one analog to digital converter. So it looks something like this. You have the ADC, but then you can connect to 8 different pins. And then this demultiplexer will just select whatever channel you select in your code. If you get a bit more advanced microcontroller, they can have multiple ADCs and also multiple channels, and there might be a controller so you can set it up to run continuously and sweep across the inputs and store them in memory, but as far as I know, the Arduino can't do that. And that's not really the point of this video anyway. I just thought I would mention it now since we're using this. Like most digital chips, you can also use it manually, so you can, instead of using a microcontroller to control which channel is being selected, you can just put toggle switches and you can select the digital value yourself. But really, if you're doing that, you might as well just use one of these. Maybe just another tip when talking about chips. When you get them, the legs are spread out so you can't put them in the breadboard. And instead of going with your fingers like this and try to straighten the pins, I find the easiest way is to just hold it with two fingers like that, put it against the table, and then just apply a little bit of pressure. That will straighten all the pins evenly. But actually I think we'll use a manual switch to begin with, and then a multimeter, just to get the idea of how it works and to demonstrate it. So let's get rid of the Arduino. And let's start by hooking up the power rails. And as we can see on the pin out here, the VSS is pin 8 and VDD is pin 16. So I'll just connect the switch up to VDD as well. So that when we turn it on, we get a high. So that is it. And then we need some pull down resistors on the other side of the switch here to keep it at 0 volts when the switch is off. And I'll just use some 22K for that. It doesn't really matter which value. As long as they're not in mega ohms and they are not so low, they will draw a lot of current. Then we need to hook the switch up to the ABC inputs, and as you can see, that's 11, 10, 9. And we can also see that up here, that A is our least significant bit and C is the most significant. Actually, I just noticed this chip has a VEE input as well. I don't know why I missed that before, but it can actually work with negative voltages as well. But it should work if we just ground this to the same signal as VSS, as long as we're only using it above 0 volts. There is a quite long explanation down in the end of the datasheet, but I didn't read all of it. It should do what we want it to do. So we'll just connect those two. And to see if it works properly, we will have to have a whole bunch of different input voltages. And the easiest way to do that, I think, would be to use a resistive divider. So we'll have our positive 5 volts up here. Then we'll just have some resistors. And just imagine there's 8 of them. And then it goes to ground. Then as long as these have the same value, we'll divide the voltage evenly between them. So in theory, we should have 2.5 volts in the middle here. And then 1.25 and 3.75. But of course we'll have 8 inputs, so it won't be the same numbers in our case. So I'll just be using 1 kilo ohm resistors for this. So our first input, input 0, is pin 13. And we'll connect that to 5 volts with the resistor. So, just like that. And then we'll go from that pin to the next one, which is pin 14, also just with a 1K resistor. And then to pin 2. And then from pin 2 to pin 3, or input 2 to input 3. And then from 3 to 4, and from 4 to 5, from 5 to 6, and then finally from 6 to 7. And then pin 3 is our common pin. So the pin out is a little bit weird here. I don't know why they did it this way, but that's what they did. So the multimeter doesn't like when you just connect an antenna, which this basically is without any power on it. But let's try to turn on the power. We are feeding it 5 volts. And we can see we're measuring about 4.07 volts on the common output now. And let's just check if that makes sense. We should have 0, 0, 0 on the control bits here, which means that channel 0 will be selected, and that is the one furthest to the positive rail. I'll just quickly measure the input voltage here just so we have an idea. We only have one digit after the decimal on that one. Oh, that's actually pretty close, so we'll just call it 5 volts. So let's calculate if this value makes sense, because it's pretty easy if you don't have that many resistors, but to get 8 outputs like we have, we put in 9 resistors in a configuration like this. We know if we have 2 resistors, then the voltage in the middle is, we assume that this is 0 volts, then it's just the supply divided by 2. If we have 3 resistors, we get 1/3 and 2/3. So if we take the 5 volts and divide it by 9 resistors, that gives us this drop per resistor, and we multiply that by 8 resistors. So that is actually not quite what we expect. I don't know why I keep forgetting things today. Of course we have this INH input, which determines if the common is connected to anything at all, and of course we need to do something about that. And we have it right here, INH. It disables all the channels, and we can see table 1. Oh, the link doesn't work. But anyway, we need to ground it, and it's pin 6. And of course I also need to ground the last pin with a resistor. It seems like I forgot that also. So it should go from here, ground, and to this pin. And now it looks more like it. So let's see, what was our value again? It was 4.44. And just to make clear, the resistor that I forgot was the last one here from the last input and to ground. So this one. I'm sorry about that. I hope it's not too confusing. So now let's go and take a look at the next input by flipping the first bit of the dip switch here. Oh, it's pin 3 of the dip switch, but I like to keep the least significant bit to the right. Oh, that's pretty tight. And we get 3.89 volts. And if we take a look, it should be exactly that. The next one should be 3.3 volts, so I'll turn this one back off and turn the next one on. And we get that, 3.3 volts. The next one, 2.77. and that is also correct. And let's just skip ahead and select the last channel. That's 0.558 or 559. And it should be 0.555 repeating, so that's close enough. It's within a couple of millivolts. So now we can see the chip works, and it's fairly precise. It's giving us very close to the value that we calculated. The multimeter we are using here have a 10 mega ohm input impedance, and that's actually important because the chip does have some resistance through it. When you select a channel, there's about, I think it's up to 200 ohms between the input and the common pin. No, it is actually more than that. If we look at the drain to source on resistance at room temperature, then you can see at 5 volts, then you can see it's normally around 470 ohms, but it can go as high as 1050 ohms. So that basically means if you're going to draw 1 milliamp and it happens to be at 1 kilo ohm, then you can drop an entire volt across the chip, and that will just throw off any readings that you can take. So in that case you have to buffer the output before you can use it. And to demonstrate that, if I go and select the first channel, and now I'll just put a wire across the first resistor here so that we supply a solid 5 volts to the input pin. That way we can measure the resistance through the chip. If I didn't do that, then we would have a drop across this resistor, and all these resistors would be pulling a little bit of current through it. We could still calculate it, but it would make it much more difficult. So I'll just put a wire across the first one temporarily. And you can see now we get a solid 5 volts. And now if I put a 1 kilo ohm resistor in parallel with the multimeter, so from the common output pin to ground, then if there's any resistance in the chip, we should see the voltage drop here. So let me do that. And indeed there is a drop. We're down to 4.137 volts. And we can calculate what the resistance of the chip is then by using the voltage divider formula. I didn't bother rewriting it, so I just solved for X. You would normally know the X value and you would calculate the output voltage, but this case it's the other way around. And we get a resistance of 208 ohms, so that's actually lower than what they specify in the datasheet. It doesn't really matter for what we're going to do that there is this resistance. We just need to keep it in mind so we don't do anything stupid. Now if we needed to do this, we could put an op-amp buffer after the common output, and then we could draw as much current as the op-amp would allow, and it wouldn't interfere with the analog switch chip. So now I'll just remove that wire I used to short out that resistor. And now we're back to the original setup. Now I can remove the dip switch and use an Arduino Nano instead to control the which channel is being selected. And then we can use the Arduino Nano to sample all the voltages and then maybe print it to the computer or something through the serial port. So we put back the Arduino Nano, and then the common output we connect to one of the analog channels. I'll just use channel 0. Then the 3 digital pins we connect to 3 digital pins on the Arduino Nano, and I'll just use from D2 to D4. So just like that. And we'll connect up some power to the Arduino, of course. And now we just need some code for it to work properly. So I'll just go and write that really quick, and then we can take a look at it. And so I'm back. I just uploaded the code that I wrote onto the Arduino Nano. And let's see if it works. It's always exciting. So I'll just be recording the screen here. I hope you don't mind. And it looks like it works. So I can't remember the exact values, but I think the first one should be 4.44 and the last should be 0.55. But there might be a little bit of an error in the reference of the Arduino. It doesn't really matter for what I'm doing. I just need a rough value of, say, plus minus 100 millivolts. That should be good enough. So now let's take a look at the code and see how I did it. And it is actually very simple. I start by defining my digital pins that select which channel should be forwarded to the Arduino. I just call them select A, B and C. Then I have a prototype for a function we'll be looking at later. I have an array to store the sampled values. And in the setup we just begin a serial connection to the computer so we can see the values. We won't be doing that in the final project, but take a look at that video when it comes out. That should be interesting. And I just set the pin mode for the select output just to make sure, and an input for E0. And in the loop here we sample all the channels. In this function down here we'll look at that later. And then we go for int equals 0 as long as I is less than 8. We increment I each time through the loop. So that will run the loop 8 times from 0 to 7. It then calculates the voltage by taking the sampled value we have in values, multiplying it by 5 and dividing it by 1024. The ADC will store the value between 0 and 1023, so we need to convert it in order to see it as a voltage. Then we just print channel and then the number of the channel we're currently at, and then equals and the voltage that we just calculated. After that, after the loop finished, we just print an empty line and wait a second, and then we repeat. And here what the sample does is that we run a loop, and again we run it 8 times from 0 to 7. And the first thing in the loop is to set the pins to the according channel. So we select the right one from the analog switch chip. And I think the easiest way to do that is to use the bitwise AND. For the least significant bit, that will be a 1. If we AND that with the channel, we'll always get the first bit. And then for the second pin, if we AND the channel with 2 in binary is 0, 1 from the right. So that will always give us the second bit. And then for the third one, we AND 4 with the channel, and 4 is always 0, 0, 1, of course. That would give us the third bit. So that's how we select it. Then we wait 2 milliseconds and then we sample it and store the value into the values array at location channel. And just to clarify how that works, say the loop has been running for a while and we're now checking for channel 5. 5 in binary would be 101, and for the A we should AND that with a 1. So 1 in binary is just 1, and that will be a 1, because 1 here and 1 there, that's a 1. For the next one we will AND it with 2, and 2 would be this number in binary, and you can see they are not both 1, so the result will be 0. And for the C, oops, sorry, that should be a 0. We will AND it with this value, and that will give us a 1, because this value match. Or in fact it would give us this value, but since it's evaluated true or false, then false is 0 and everything else is true. So that's how it works. And if we just remove that, you can see this gives the same as this up here. We just split it onto the different pins. So that's about it for this video. If you liked it, please give it a thumbs up on YouTube. And make sure to check out the video where I make the actual lithium polymer battery voltage alarm, or whatever we should call it. Anyways, this was a quick look at the CD4051 chip, and I hope you liked it. See ya.